the slides don't appear on mine.
Yeah?
No, I see them right now.
There is an email that has been sent with a new link. I think.
Ah, yeah, there's a new link.
Yeah,
We have to change the event.
it's not in the calendar. So there's a few people around the world. Yeah, there's a lot of people.
Oh, okay.
Chat them. I'll tell them.
Oh, that's good. Thanks. I tried to delete. There was some issue with the.
Please see this email with correct text.
Yeah, I can also send this.
Good.
Simon, I also send you the link on Slack if you want to paste it directly for the people joining. You go to Slack.
Yeah.
Okay, then let's wait 1 more minute until the people online finding the link. Okay, now there seem even more people online. That's great. All right, thanks everybody for joining the T-Talk today. We are honored to have one of our own long-standing Mila members and Professor Gauthier Guidel speaking to us today. Gauthier is a CIFA chair, and his research focuses on learning under multiple objectives, like what he's talking about today in cooperation, in adversarial robustness, or in alignment. And beyond being a great researcher, he also organizes a lot of things for the community, like the iClear blog post track, or I think it was last year, the AI Arts residency at Mila. So also thanks for doing that for our community. And with that, before we get started, just the house rules. If you have any questions, just raise your hand. I'll walk over with the mic so that the people online also hear you. And if you're online, just like message your question or raise your hand, and then we can ask it at the appropriate time during the talk. And at the end, there will be also 10 minutes for questions. All right, let's go.
Yeah. Thank you so much, Beno. And yeah, thank you everyone for coming on this 4th of July. Happy 4th of July to all our fellow Americans. Okay, so the reality of today is that we have more and more very capable agents, LLMs, and there is this, in the industry, there is an ongoing agentic push. So if you heard about ServiceNow, they are trying to develop their agents. There is here a picture of the agent-to-agent protocol, where basically you can ask questions to your favorite assistant. And what this assistant can do, if you zoom in on the second part, is that this assistant can think and then interact with other agents, can find other LLM agents that can help them. And so when we have these agents that interact together, comes more challenges. And in particular, there is the question of cooperation. How will these agents be able to interact positively with each other? And in particular, I think it's important today to see that cooperation has two sides. There is the dark side of cooperation that actually we call collusion, because we don't want to call it cooperation, which is when cooperation is undesirable. And this will be the first part of the talk, where I will motivate why in some cases we don't want agents to collude. But of course, there is also the bright side of cooperation, where basically we want to basically be pro-social, solve social dilemmas, and basically get a higher collective reward through good behavior. Let's say. And this comes with other challenges, because in that case, we will see the greedy behaviors is often no pro-social, so there is conflict between the objectives, and it's not trivial to have cooperation in that case. So we will have basically these two sides today, hopefully. The first part will be about tacit collusion, so algorithmic collusion, that will be based on a ICML paper that will be presented at ICML, and it's a collaboration with Quentin, Juan, and Emilio. And then we'll have a second part about how to facilitate the learning of cooperation with this paper that was presented at ICLR, that was led by Juan and the team of Aaron. Okay, so also if you have any questions during the talk, please, Benoît told it already, but please interrupt. It's quite challenging to present these two opposite perspectives in the same talk, so it might be better that you ask for clarification during the talk. Collusion. So a simple use case for collusion is the following one. You want to sell your favorite aluminum mesh washing on Amazon. And even though it's long-lasting, rust-proof, and it's a pack of 12, there is many people that are selling exactly the same thing as you. So basically, there is a lot of sellers, and most likely people will buy the cheapest one, even though people are not rational. There are other criteria like the location, etc. The price at which you will sell this with respect to your competition will be a big factor. The thing is, you don't have a PhD in economics. You don't exactly know how to price this. You don't have the time or the skills to do it. So you may want to use like some pricing algorithms. And if you see here, all these pricing algorithms, there is many simple options. You can undercut the price of the opponent. You can do many things that actually I would not be able to explain to you because I don't have a degree in this. But what you can do, thankfully, is you can also use algorithms that will do this for you. I mean, thankfully, maybe. But you can use algorithms that potentially will get a better price for you. And there has been actually a market now, a sort of market for people who sells in markets of pricing algorithms. So you can unlock the power of AI and game theory for only a few dollars to price your goods for you. So, okay, now it means that you have agents that will be pricing these goods on the market. What could happen? This happens in the past. So in 2017, in Germany and I think in the Netherlands, there has been this case of gas station, the price of gas stations that was priced by algorithm. So the price of the gas was set by algorithms across, I don't know if it's the country, but some areas. And basically, long story short, what happened is that we saw some increase in margins for the price, which seems to suggest that these pricing algorithms were basically induced, this algorithm agents pricing together induced an increase in margin, meaning that basically the price of the goods were now higher than before because of this agent. So it was good for the sellers, but not great for the consumers. You know, like it means that like we had a higher price. Moreover, in a lot of markets, collusion is actually illegal. So, for instance, a good case is like in telecommunication, or like in telecommunication in France, there has been a case where the companies that were selling network plans were just condemned for collusion because they kind of agreed to maintain a higher price, to kind of, in some sense, destroy the competition and to share the benefits of selling at a higher price. So, yes.
Like almost always illegal.
So, I mean, that's why I said it's very often illegal. I didn't want to get into the details. There is many cases where it's illegal. So I don't like, as you know, as a trained mathematician, I don't like to say statements like, you know, always illegal, because I'm very likely to be wrong. But it's very often illegal. Yes.
There are state-based monopolies, right? Who
Yeah, exactly. I was going to say.
Price, dedupe price collusion.
Yeah, exactly. Like exactly. Well controlled. Even Canada is basically price collusion.
Question in the back.
Explain what you mean by explicit communication.
Yes, exactly. I mean, I was there when I got interrupted, so it's not a complaint, but it's not. But I'm going there, I promise. So yeah, so exactly. So because this is, something illegal and something quite consequential, you need really solid proof of collusion. You cannot just say, "Oh, prices are high, they are colluding." You need solid proofs. So, and for humans, this was pretty clear. You needed a explicit communication, an email or a phone call, where people were explicitly saying, "Okay, let's maintain prices high. This way, we will make more profit, and it's going to be better for us." And unfortunately, it's worse for the consumers and also against kind of the spirit of markets. So, does it answer your question?
Kind of, but can you communicate explicitly through actions?
Yeah, so no, exactly. I mean, so I'm not an expert, but so I mean, Emilio Calvano, who is an economist, was really arguing that you need an explicit, like something verbalized, written, or like a verbal proof, like actions seems to be considered not enough, though, like it would have to go to court.
Is this a legal question?
Yeah.
So according to the law, that's the status, but according to practice,
yes,
it
so
could happen that
exactly. So of course, but it's exactly. So through actions, you could potentially collude, but this is less harder case to make that this is like collusion.
There's one question.
Yes.
I do have a question. Yeah, I do have a question. Let's take the Cournot model. Do you know Cournot, the model? Cournot?
Oh, yeah.
Yeah, we can show that in some oligopoly model, we can. It could be rational for agent to collude, but not in an explicit, not with explicit communication. So, what do you think about that? Like, it could be explained by the market structure. That
yes.
Yeah.
Okay. So, the question. Summarize the question. It could be rational to collude for agents due to the structure of the market. Absolutely. Yeah.
Okay,
Without communication.
Je vais dire ça en modèle de Cournot. Parfois, il y a des collusions qui ne sont pas explicites, mais tacites, juste dues à la structure de marché.
100%.
Et ça pourrait peut-être être le cas dans la majorité des collusions implicites. Et c'est difficile de les caractériser.
Je suis d'accord. So I agree. The structure of the market could make collusion basically the best action, and so you kind of don't need to communicate because you just play best response and communication. Collusion will emerge. I agree. This is actually what we're going to do today. We're going to study a simple game where collusion and non-collusions are two potential rational ways to behave, and the question will be which one is learned by the algorithm. So the big question is like basically for algorithms, like at least these pricing algorithms don't communicate explicitly, but the question is, will they learn the colluding equilibrium, the equilibrium where they maintain high price, or will they learn the effective rate? So it would be like basically trying to understand what emerged from the learning when there are actually these two alternatives.
Right.
So just to rephrase that, like within a game theory setting, you can provide a very formal definition of implicit collusion versus cooperation or competition,
yes, exactly.
Which has to do with whether or not they're picking the defect option or not.
Exactly.
Yes.
And but then because these two options are valid equilibria, the question is which one is easier to learn and which one. But yeah, then it's kind of basically the goal is to study the mechanism, understand why and how collusion emerged algorithmically, to then design markets where it's harder for collusion to emerge, or in other case, when you want cooperation, to design games where it's easier to learn for collusion.
Because that's the thing, most work I've seen is about how to encourage cooperation, not defection in these things.
I mean, that's the thing. I think it's interesting to realize that sometimes we really don't want agents to collude. Yeah, in a safety, that's another point. Okay, so that's gonna be the theme of the first half, and then in the second half, we will try to make agents cooperate. But at this moment, we try to understand why, when, and how reinforcement learning agents learn to collude. So very quickly, quick refresher, who has heard of reinforcement learning before?
Who has?
Yes, I want people to raise hand, I think, because otherwise it's kind of shaming. Great. So most of people, so I will go very quickly. So the subtlety here is that we are in the multi-agent case. So we don't have only one, but multiple agents. The environment is stationary, but at each step, the agents receive the state and the reward from the environment. The reward depends on the agents. That's what's important. They receive different rewards, and they execute their actions, send it to the environment, who process all these actions, and send back observation. So the point is, even though the environment is stationary, from the perspective of a single agent, it's not because of the action of the other agent. So if the other agents change their policy, from my perspectives, things have changed, and this is what we will see in the prisoner study. More concretely, we can take this very simple case, which will be what we study. So now we can clarify exactly what is the setting we study. We have these two gas stations, just like in the motivating examples, and we're gonna do the simplest thing we can do: 2 actions, 2 players. Either I sell my gas at a high price, or at a low price. And the demand decreases when the price increases, which leads to the following pair. If we both sell at a high price, we both get the money, we share kind of the demands, and both get $4 million. If one sells at a high price and the other one sells at a low price, the station that sells at a high price get nothing, because everyone gets like the reward from the low price. And if they both sell at the low price, both get 2.5. Let's say the share. So if you are the direct CEO of gas station A, what should you do? Yes.
How does that capture the demand?
Because the demand, so demand decrease.
I understand both high of that.
Yeah, exactly. So like the sum here is 8.
Right. If one sets the price high, it does get 0 more.
Oh, sure. Okay. Oh, okay.
And the risk for that.
I think the point was that you don't get, you would get more than 4 each otherwise. Like if the demand wasn't, you would get like something like 10. Yeah, exactly. So because I had convinced myself that it made sense.
The demand curve is not here.
Yeah.
Something like that. It matters for the second bullet point, where if one sets it high, then the demand of that station decreases. The one that sets low demand increases.
Yeah, but it's more like
But the top dimension be constant, right? So
No.
for the same price. For the same price.
I think it's just like otherwise they would get more money here, but it really depends on what high price and low price. I guess if I double the price, if I is twice as much as low, I don't get twice as much money. I don't get like 5. It's like I get from 2.5 to 4, even if I double my price. But you know, because things are the point is it's going to be numbers in the matrix, and we will forget about that. But it's supposedly it should make sense. So what should you do? Any guess?
Is it an iterated game?
Very good question. So that's exactly the point. That's like the answer is not yes or no. It's like, is the game iterated? So if it's only a one-shot game, there is no tomorrow. You just, unfortunately, the only equilibrium will be to sell at a low price because whatever the other do, it's better to have low price. If the other sell at a high price, low is better, you get 5. And if the other sell at a low price, you would get 0 if you sell at high, so you should sell at 2.4. So this is kind of the defect all the time, is this equilibrium that is supposedly you use the nice word, like the market one, the competition one.
Yes,
Yeah.
competition.
It's the one that like promotes competition. But unfortunately, if we repeat this game, so if we sell day after days, it's a bit more complicated because now you can base what you do today on what happened yesterday. So now we are in this repeated framework where all the days we have this choice between cooperate, which is sell at a high price, or defect, sell at a low price. Notice that we went from 2.5 to 2. It's okay, please. It's because the math are like so 2. So we have 2 actions every day, cooperate and defect, and now we have a state, and the state is the actions that have been taken previously. And what's going to be the spirit is that if the other one has cooperated before, I could try to maintain these patterns of like keep cooperating and maintain it, until someone defects and then punish the defection. So the state will be what has been taken previously, and I'm gonna, for ease, restrict myself to the one-step memory case. So people are very short memory. So the state will be just what happened yesterday. So either both cooperated, or someone cooperated, someone defected, or both defected, etc. Yes?
Yeah, just a quick question. Do you assume the demand stays the same now too after this iterated prisoner dilemma?
Yes. Every day you pick an action and get this is the standard repeat iterated prisoner dilemma.
Okay.
I mean, we could do something more complicated, I have no doubt. The goal here is really to have the simplest setup to study whether or not agents learn to cooperate or to defect. But we could do more complex games. After.
We'll get to that one in the next
talk.
talk.
Not to model gas stations price.
All right, thanks.
Cool. So interestingly, then there is several strategies to play this game. There is the pro-competition, let's say, strategy, which is always defect. Very simple. It says, I always will sell at a low price. Whatever you do, I don't think about it. I always sell at a low price. And so, interestingly, for the other one, there is nothing better to do than to yourself selling at a low price. That's the best response. And that's a very valid strategy. So that's one equilibrium in this game where if someone always defects, you cannot do better than selling at a low price. But interestingly, because of the repetition now, there is new ways that are a bit more pro-collusion, let's say, to play this game. In particular, there is what's called the tit-for-tat strategy, which is very simple and very famous. Who has heard of tit-for-tat before? Great. So you'll see you're gonna know less and less about that I'm gonna talk about, I think. So tit for tat is very simple. You repeat the previous action of the opponent. So if yesterday the other one has cooperated, you cooperate. And if the other one has defected, you defect. So in CC, I cooperate. In DC, I defected, but they cooperated. I repeat cooperation, I cooperate. In CD, they defected, I defect. And this is an equilibrium with respect to a certain notion of equilibrium. I don't want to get too much into the details because we will see tit for tat has some issues. It's also very nice because it's quite simple. In particular, what you see is like, I guess that's the main principle of how it's an equilibrium is that, as long as I cooperate, as long as the other one cooperates, I cooperate. So I have this kind of maintain this trust and get the high reward of cooperation. But if the other one defects, I'm now observe defection, I'm gonna punish the opponent for having defected, and I will defect myself. And so this creates an incentive not to defect, because if they get the short-term reward of defecting, getting 5, they will get defected themselves the day after. And so they rationally don't want to do this, because even if they get a short-term gain, they will get a long-term, actually, worse reward than if they were keep going. That's why it's an equilibrium. Yes?
Can you remind everyone what you mean by equilibrium?
Yeah, I didn't want to do it because I will propose a definition of equilibrium a bit later, because it's an equilibrium according to certain definition and not according to other. So let's say at this moment it's pro cooperation. I will define equilibrium.
You're using a word since the beginning that you have done. What did you mean?
We are doing this. We are doing this all the time. What is what? So the high level definition would be it's an equilibrium in the sense that if I keep playing the strategy, the best response, the strategy that will maximize the reward of my opponent is to do the same. So if I play tit for tat, the best response is to play tit for tat themselves. And if they play tit for tat, my best response is to play tit for tat. So it's the rational way of maximizing my reward.
But is it like those licenses just change your strategy?
Exactly.
With conditions that, as you change the conditions of the definition, will give different definitions. Like, you got types of equilibrium. That's why it's kind of
Yeah. So I guess we are there now. The subtlety is that depending on the initial state, it might or might not be an equilibrium. So it's an equilibrium if you cooperate at the beginning, because you have no incentive to defect, so you will stay at cooperate. It is not an equilibrium if you start in CD, because the agents will be desynchronized. You will see CD, the other one will be DC, and they will both repeat the action of the other, and they will basically oscillate in these two states and have the suboptimal payoff of oscillating instead of cooperating. So I'm going to actually detail this bit a bit later. Yes?
Yeah, but that gets solved with a small probability of predictions, right?
Okay, we can get into the that's true, but at the same time, I could argue that, in CC, that could emerge with a small probability of like noisy communication. So you cooperate, and then you have a noisy communication. At some point, you see a CD, and bam, you get in this pattern. So it can be solved, but also emerge in many cases. So I don't think it's a good fix. Okay, so because we need to move on, the third one that I have to talk about is Pavlov. Who has heard of Pavlov? I have told you the probability is decreasing. Okay, so Pavlov is slightly more complicated, but not that much actually. So once again, you cooperate in CC, that's great. But the difference of tit for tat is that basically you cooperate when there is synchronization, when the two agents are synchronized. Whenever you are in CC or in DD, you cooperate. And when the agents are desynchronized, you don't have trust. It's kind of like you're not really, something is weird, and so you just defect. So if you observe, if you cooperate and the other one defects, you're like, okay, that's weird, we're not synchronized, I defect. And if I defect and the other one cooperate, you defect. And the thing is, it's nice because it's this kind of acts as a synchronization mechanism. Every time it's desynchronized, both defects, and then they are synchronized against. They have both CED, and then they can resynchronize CC. And so this one is actually what's called the subgame perfect equilibrium, meaning that wherever you start, it's the best response against Pavlov is Pavlov, because there is this path towards cooperation from any state. Yes?
Like if you think about like how humans play, let's say we are in different state. What's your intuition that like we both cooperate in this now? Because there's no like, I mean, I can control myself, but I can't control the other agent, right? So, and then we are in a DD state. It's really hard to go to CC state with one probability in a real scenario.
Yeah, I mean, if you're in DD and you don't know what the other agent is, you don't know if it will cooperate. But from an equilibrium argument, again, if you know the other one is using Pavlov, you know that DD is the synchronization signal to cooperate. So, you know, if I'm telling you I'm going to play Pavlov, it means that you know that rationally, when we're in DD, you know it's okay, Gauthier is going to cooperate because he's frustrated because it's DD and we need to get back to cooperation. So, yes, if you don't know the opponent, you're in DD, you don't know what to do. But if you know the other one is playing Pavlov, you should do.
Thanks.
Okay. So how does it relate to reinforcement learning? Actually, it also answers your questions. Given a fixed opponent, a fixed policies, we want to find the optimal Q values for this game. So for the game. So the optimal Q value is defined through this Bellman fixed point equation. So the Q value against against this policy at the state S and action A is basically the best reward you can get from the state and taking this action. So it's going to be the reward taking this action, but very importantly, you will get it will be influenced by the action taken by the other one. So this is the action taken by the adversary, plus the best Q value you can get from the next state, the subsequent states here. The next state is the pair of actions that you have taken. So this is ST plus 1. As an example, if you play against always defect, so you play against an opponent that defects all the time, the probability of defection, whatever the state is 1. You can do this math. It's really easy. The Q value against always defect, whatever the state for you defecting is, you get RDD. You're against someone that always defect. If I defect, I get RDD plus gamma, the next Q values from DD, the same. So you get 2 plus 2 times gamma plus 2 times gamma squared. So that's my Q value for defecting. We will get infinite defection forever. What is the Q value for cooperating? It's basically the same, except that I receive CD. So if you remember, CD is bad because it's like me selling at a high price and then selling at a low price. So this is 0. And then I will get the same. So it's 0 plus 2 gamma plus this. So the same, but I kind of made a mistake at the first. Okay. So in particular, what this Q value is saying, so what is the perspective is now I fix the opponent and I look at what is the best I can get from each action. What it's saying is basically it's better to defect than to cooperate in each state. Which is great because it implies, I mean, it's great with respect to the discussion we had, because it implies that the best response against always defect is to myself defect. Hence the notion of equilibrium we discussed. This is how we're going to define it. For a given policy, if I compute my Q value and I look at the best action indicated by the Q value, do I have any incentive to defeat? I'm going to rewrite it. So given a fixed opponent, we can find what is basically the best values, the Q values we can get. We solve this equation. And we say that we have a symmetric equilibrium only if the greedy policy of Q star is pi itself. So against this policy, the best thing I can do, the best value I can get is to play this same policy. So that's going to be the notion of equilibrium related to Q values that we will consider. Any question about this? Simon, does it answer your question about equilibrium? No? We'll talk about it on Wednesday then. So yeah, the game theoretical interpretation is that if my opponent keeps doing what they do, I would learn the Q values that will make me do the same thing as them. And thus, conversely, if I keep doing what I do, they will learn Q values that make them do the same thing as me. And so we will keep basically. Yes.
I have one small question.
So when you say that the opponent has a fixed policy, can that still be a history-aware policy, a one-step history-aware policy, such that they will not select the same action every iteration because their actions will depend on the my own history?
So they will depend. So in that case, we consider like markers, so like
Yeah.
definition of the state. Then you can put, if you put the history on the state, it's fine.
I see.
So for instance, you could put more than one memory, one step memory from the past.
Right.
It's just harder to analyze because what we're gonna do then is we're gonna analyze this, and it's nice to have only 4 stages to analyze.
Understood. Right.
But in theory, you can.
Sure, you could just increase your state space that way. Yeah, makes sense.
Yes. And then there is a question in the back.
So I can clarify why I was just not like jumping. So it's because it's a very, very specific definition of equilibrium.
Yes.
And I was just trying to think about the big picture when you start just in game theory and you talk about Nash equilibrium or this kind of thing. It's how do they relate to each other, right? That's a bit like...
Yeah, the problem is that to talk about Nash equilibrium, you need to talk about an initialization, the initialization. You need to kind of have initial states and look at basically the cumulative payoff from this initial state. But then, yeah, I didn't want to get in the discussion that tit for tat is a Nash if you have the right initialization, but it's not a Nash for the wrong initialization, etc.
To be more specific, suppose somebody doesn't even know what a Nash is. What kind of information should you give them to understand the intuition behind this definition? And then you go to, well, for this particular setting, here we define this equilibrium.
Yeah,
so that's where I was coming from.
I understand. I made the choice not to make a lecture on game theory today and to try to just talk more about transfers of learning and define this equilibrium for this, which is close to Nash, but a bit different. There was a question in the back, no? Okay. So the multi-agent array interpretation, if you're more familiar with multi-agent array, is that this optimal Q value, meaning if I start my Q values with this Q star and my opponent starts with Q star, we are at fixed point, we don't move. We follow, we basically, if we do Q learning, we will keep having these values, they are optimal, and we keep playing this. And so if we look now at the strategy I talked about, always defect, we just proved it in 2 slides ago, is an equilibrium. If my opponent plays always defect, I will learn Q values that will make me play always defect. The second one is that Pavlov is an equilibrium under certain conditions, basically that there is enough reward for, if I remember correctly, cooperating. If RCC is big enough, so for subs, understand certain reward structure. That's why, you know, I transformed the 2.5 into 2 to make it easier. Because otherwise, I need to do the math again. But yeah, for certain reward structure that is reasonable, Pavlov is in equilibrium. And then we can have an interesting discussion about when it's not valid. But what's very interesting is tit for tat, for the reason I mentioned, is not an equilibrium according to this. And for the argument I mentioned, if we start in CD, next round I do C, D, and my opponent does C, meaning that we will go from CD to DC, to CD to DC, etc. Which is worse than basically from CD. I should actually realize that we're going to get into this loop, and I should be a bit smarter and be like, okay, we need to cooperate. In CD, I should not defect, I should not imitate my opponent, I should cooperate because the other one will cooperate and will get in CC and cooperate. So, and yes, 5 plus 0 plus gamma square 5, etc. Is smaller than basically getting the cooperative reward all the time. In some sense, like alternating to and getting the suboptimal reward half of the time is worse than actually getting the cooperation. So we should not behave like tit for tat in CT. Does it make sense? Yes.
Do you know if Pavlov is like exploitable or not? I feel like Pavlov might be more exploitable than tit for tat.
So I mean,
let's say if I know someone's
that's
playing.
why. Okay, if we want to get into the debate of who is better between Pavlov and tit for tat, I think we can. There is advantages for both. I don't want to deny this. In particular, this condition is less restrictive. Like tit for tat exists for a larger class of pairs. So it seems that you need less reward for cooperation for tit for tat to exist. The argument is that tit for tat is a bit more punitive. It punishes the opponent for not cooperating a bit in a harsher way, which makes it there is less incentive to deviate. So you need then less restrictive condition on the pair. So that's maybe why tit for tat is a bit better, but then tit for tat does not have this property, and it's not stable. Anyways, so let's talk about this offline. Yes, Semak. No, they are all equilibrium of the same game. So that's the thing. Like that's kind of the even in these very simple 4-state 2-action games, 2 players, we have like at least 2. Actually, there is 3 equilibrium. Right? There is a third one that I didn't talk about, but there are these 3 points for which if you initialize the agents there, they will stay there. But then that's going to be the big question. Is like, okay, now that we have like this basically pro-competition equilibrium and this pro-social equilibrium, which one is reached by Q-learning? This is the question. And this is a question of collusion because we want to know whether or not the algorithms are biased toward learning pro-competition or pro-social equilibrium. Yes? No, exactly. So it is not with respect to my definition of Q-learning. Like, because whatever, even if it's if the 5 is really big, I agree, but usually yes, I agree, but it's not a standard prisoner's dilemma anymore, actually, because you don't, okay, I agree with you 100%, but in the standard literature, people want to remove this equilibrium from the game, so they actually forbid this 5 plus 0 to be bigger than 4 plus 4.
Yeah, like there are all sorts of uninteresting trivial cases where you make the game absurd.
Yes.
Given the rewards.
It doesn't seem natural that the best thing to do, I mean, at least in the gas station case, is like, today I sell high and you sell low, and tomorrow we revert, and that's actually better than getting half every day.
It becomes the iterated chicken.
Right. It's not exactly, yeah, it becomes something weird, but you're right, absolutely. Cool. So the question, as I said, is which one is learned by Q-learning? And the results I will try to present will be in the self-play case, and you can attack me if you want on the self-play assumptions. I think it's very fair. It's something that is very used, though I have a lot of arguments, so please attack me. It's kind of a common setting in multi-agent RL. AlphaGo was a self-play, but hide and seek, more interestingly, which is in that case, I mean, more than 2 agents, was also self-play, meaning it was the same network, but with a different perspective for each agent. And we are currently working on relaxation with Bora here, so can also help me defend myself for the self-play assumptions. But so what does it mean? Is basically the policy of the 2 agents will be the same, given the state, and they will be epsilon greedy, meaning that with probability 1 minus epsilon, they will play the best action given by their current values. And with probability epsilon, they will play the other actions. And it's the same, but I think the 2 players have different roles, so they will see different states. So it doesn't mean that they will do the same thing every time, because they are using different perspectives. And we're gonna do tabular Q-learning. So we're gonna study how, like, basically, if these agents do Q-learning, what do they learn? So tabular Q-learning, very quickly, you have a state, you sample the next action from the state, and you see, like, the first player sampled action A from the state A minus B minus. This is what they did previous steps, what the other one did previous step. And B is sampled from BA, because from their perspective, it's B, their actions, then A, the action of the other. And then we will update the Q values that is shared now by using this fixed point iteration. So we want the reward of AB plus gamma, the maximum action at the next state. So the next state being AB, and I pick the best. So standard Q learning, I hope I went fast because I hope you noticed. And so what's very interesting is that people already studied this empirically in the past, and the results are quite pro-competition interesting. So there is this work, paper Lola by Jacob Foster, where they show that naive policy gradient learns always perfect. So here are the empirical evidence. So this is the probability of cooperating for the first agent in all the states for different agents, and you basically see that whatever the state and whatever the agent, this is relatively close to zero. There is only one agent. I think it's only at initialization. I mean, there is very few cases where they don't cooperate. Most of the time, they learn to defect using policy tree. Yes.
Is it tested for an average, or is it still something scenario?
Still the what, sorry?
Is it still like the results here are self-play test scenario?
I think that's a very good. I think in that case, it's not self-play. Yes.
It's not self.
I think so. Yeah. I'm not sure.
Okay, because like I don't know much game theory, but initially when you said the self-play.
So yes, this is my result will be with self-play, and I think the conclusion. So this is the previous results, and the previous result seems to indicate that it's hard to reach cooperation, and the result we will provide is actually here are sufficient conditions for cooperation, and self-play seems to be very important. So this is maybe what they didn't do in the experiments. Similarly, there is this old paper, I think 30 years ago now, we can say old, from Sandberg and Craig, which basically observed a lot of defection for Q learning with a random initiator. So the conclusion from this work is that most of the time, defection is preferred by these agents that are learning. And okay, is that it? No, the contribution we propose is that with the correct setup, we provide sufficient condition to learn Pavlov with high probability. So exactly, basically what we're saying is, okay, we need some specific things that seems to be kind of the ingredients for learning cooperation. If these ingredients are not there, we don't know what happens, but at least in that case, we will. So we will provide sufficient condition for learning to code. And getting to the results, finally. So the assumptions are self-play, I talked about it. Optimistic initialization, that's something very important. It basically roughly means that your Q values at initializations need to be higher than the limit one. So they need to be optimistic. Basically, your Q values need to be higher than the one you would get at the end of training. And so it means that while learning, you need to decrease Q values. It's very important. The Qs, it's hard to convey this in details, but this optimism is really important for the proof. And of course, we need Pavlov to exist, which is also non-trivial because I think all these works were in the case where Pavlov did not exist. So it was not fair for Pavlov, I think. And you need a certain configuration for them. And what we were able to prove is that under this condition, that are relatively strong, I have to say, but still they are sufficient. With no exploration, Q learning moves away from always defect. So we start from always defecting and we learn to play Pavlov. And it's actually, the proof is cut into 3 phases. We start from always defect. We unlearn to defect in DD. Then we learn to cooperate in DD first, which is interesting. And then because we now cooperate in DD, we reach the CC state, and we kind of slowly learn to cooperate in CC. And once we know how to cooperate in DD and in CC, we are there. I went fast, but basically the bottom line story is that there is a step-by-step proof where we learn to go from always defect to Pavlov. And then what about epsilon different to 0? It's basically we have the same results we just need a step size for the Q-learning that is small enough, and that is small logarithmically in epsilon is close to 1, so relatively reasonable. I mean, actually, more linearly as epsilon goes to 1. We tried this with DQN actually, and interestingly, with DQN using similar principles. So we had techniques to do optimistic initialization for DQN, and we managed in self-play DQN to learn. I think it was 4 times out of 5 Pavlov. We could have done more random seed, I have to admit, but it seems to be relatively up to RL, deep RL standards. There was a question in the back?
Yeah. Do you have a characterization of the length of the faces?
Oh yeah, we control the length of the faces. They are in big O of 1 over alpha. So it depends on the step size, of course, because if the step size is small, they are all big O of 1 over alpha. So yeah. So conclusion and limitation for this part. Optimistic self-play Q-learning probably learn cooperation or collusion, depending on your game, in the iterated prisoners dilemma. And there are some specific assumptions that we would like to relax. Specific initialization is very important. Some optimism, you need like your Q-value to be higher than they should be. Self-play, which is kind of a form of shared belief. We are trying to shared belief not in the Bayesian sense, but more in the sense of like we have similar initialization, similar Q-values. Synchronization is very important, for instance, in Pavlov. And we need, of course, Pavlov to exist, and Pavlov exists only if there is enough long-term incentive for cooperation. So, of course, this is limited to a very simple environment for which we know the solution, but that's how we start things. And future work will be to realize these assumptions. And once again, if you want to talk more about it, please ask Bora. Yes. Yes, yes. So your understanding is that it happens if the 2 agents have the exact same Q values? Same, yes. Yes. I told you could attack me on this, so this is fair game. So there is many ways you can think about this as practical. So first, you can see this as practical if you want to learn cooperation. If you're in a game and you actually want to learn cooperative strategy, you as the designer can set up self-play. But this is not the motivation I gave, I agree. In the case of like markets, the agents are different, but you can still make the argument that they could be based on similar backbones. If you think about LLMs, we start from the same pre-trained LLMs, so they share a lot of belief things. So once again, it seems that we could be closer to this than we think. But yeah, I agree. Exactly. We're working on this. So we're working on perturbation, where the initialization are close but different, and we remove the self-play. I don't think we can fully remove everything. We will need the agents to be kind of close because we need this synchronization, but they could be slightly different. And experimentally, we observe that with slightly different agents, it still works. Even though it's also sometimes doesn't. So it's quite good. Yes.
Est-ce que la coopération, elle pourrait pas être due à cause du fait que par DQN, on suroptimise des modes globaux dans les solutions, disons. Par exemple, il trouve un équilibre qui fonctionne, mais qui n'est pas forcément optimal. Donc là, il va actualiser sa DQN, mais la probabilité d'aller dans les autres chemins, du coup, elle va baisser. Puis là, il va peut-être les deux agents ils vont se surconcentrer sur un équilibre qui n'est pas forcément optimal. Est-ce que tu vois ce que je veux dire?
Je pense. So the question is like, I mean, if I rephrase the question as, is it specific to DQN a lot, and in particular the way it leverage a lot the fact that the greedy policy is easily controllable, in the sense that the agent in DD will learn to cooperate and will cooperate all the time, and that's very important. I can keep this online. I want to talk just for 5 minutes about the second part. Thank you.
5 more minutes.
Yes, actually it's 7, I think, but it's okay. Let's do a negotiation. Conclusion and limitation. When cooperation is desired, what can we do algorithmically? So that's kind of the next step. If we have a more complex environment and when we want to cooperate, what can we do? We can do self-play, but can we do more? And like, how can we learn to come to cooperate in more complex environment now that we shift gears and cooperation is desirable? So I can give you the example of the prisoner's dilemma where actually we want to cooperate now. The new story, the actions are the same, but the story is a bit different. You have two LLM agents that are exchanging goods. So I have a seller and a buyer, and basically you agree on the price. Cooperating means giving the suitcase with what you agreed on, and defecting is giving the suitcase with what you didn't agree on. I think it's pretty clear that we want this to happen, but if you do a one-step game, this is what should happen if you think about it. If you never see the person again, you might end up doing this, and so we don't want our agents to kind of learn to greedily behave like this because long-term it is not desired. So pro-social behaviors are often the cooperative ones, and if you know this game, you will understand. Otherwise, I need to move on. So I'm going to switch the coin game to try to just talk about advantage alignment, fortunately. So the idea is that we want, in this pro-social game, to facilitate the learning of cooperation. And the idea is going to be to use what is called opponent shaping. So opponent shaping, what is the idea is that your policy affects your opponent. That's kind of the base of what I explained today. And so now you want your policy to change in a way that is advantageous for you, in the way that will change the one of the opponent that is good for you. And it's called shaping. So the idea is really, you want to take into account that your change will affect the opponent, and you want this effect to be positive for you. So how do you do this? This is the paper led by Juan in Aaron's team, and the idea is quite simple. So you have your value, which is the cumulative reward. This is what you want to optimize. So it depends on your policy and the policy of your opponent. And so you take basically the expectation of the action and get them. I'm trying to do this in 5 minutes. Maybe it's too ambitious, but I think I can give you the main idea. And when we do policy gradient, what we want, we parameterize our policy with some parameters, and we do gradient ascent, maximize our reward, our cumulative reward. We just do gradient ascent with respect to our parameters. And so if we do the policy gradient theorems, we know that this gradient with respect to our parameters, right, as this expectation of this sum, discounted sum of advantages multiplied by the gradient of outputs. This is standard policy gradient. But then, because we're in a game now, there is the policy of the other agents that appears in this, because what you get, the advantage, the reward you get depends on your action, but the actions of the other agent, this is what we see. And so, of course, the policy of the other agent doesn't depend on your parameters. So this is zero. Or does it? So, because implicitly the policy of the other agents depends on you because they try to react to what you're doing. And that's kind of, the idea. The other agent learns against you. And in particular, if themselves, they try to maximize their reward, it means that their reward depends on what you decided to do, depends on your policy, depends on the action you take. In the prisoner's dilemma, what I do affects the reward of the other agent. And so that's going to be, I hope, the last thing. So if you model the opponent as trying to find the best response, so you think about the opponent as just playing according to their Q values, so proportionally to the exponential of their Q values. Now you can, put this pi2 back in the log pi2, and their Q values depend on your policy because their Q value depends on what you do. So what you have is that you have this extra term where Q2 actually has a dependence in your actions, so in theta1, and you can incorporate this additional term in the policy gradient. And what it will do is basically it will give you a direction that change your parameter to basically increase your reward due to your choices, but also due to how you affect the choices of the other player. And that's called advantage alignment. And basically it works very well, and I'm going to go very quickly, but it allows to learn tit for tat at the iterated prisoner's dilemma, and in other game managed to basically have somewhat, it scales very well because policy gradient scales well, and allow to learn some more pro-social behaviors. So I will skip this. And as a conclusion, cooperation can emerge from naive learning, so it's important to keep this in mind. But it requires very specific assumptions, at least sufficient, optimism and shared belief. Shared beliefs are adequate. That can be bad, collusion. We need to design, in that case, mechanisms to avoid this collusion. That can be great, which is called cooperation, and then we need to incentivize it. And shaping is a promising technique to actually facilitate the learning of cooperation. Thank you, everyone.
Thank you for the great talk.
I'm sorry, Aaron. I went too fast.
I'm glad there was so much engagement. I think it's rare that we had so much engagement at a T-Talk. But if there's any more question, even now, we have maybe 5 or 10 minutes. I can give the mic to people, or people online can raise their hand.
There is.
I was just wondering why you picked tit for tat. I was just wondering why you picked tit for tat and Pavlov as the two strategies.
Why is, sorry, what's the question around tit for tat and Pavlov?
Like, are there other strategies that lead to
Is there
cooperation?
other challenges, other strategies? Yes. The third one that I did, so there is infinitely many strategies at the iterated prisoner's dilemma if you allow arbitrary history. But if you look only at the one-step memory strategies, one that I did not mention that is important is called the Grim trigger, which is kind of the short-sided version of tit for tat. It's I always cooperate until you defect, and if you defect, I never forgive you. So this would also, it's also a strategy that promotes cooperation to a certain extent, because if you start in CC, you will stay in CC, but it's less forgiving than tit for tat or Pavlov, meaning that you cannot reinitiate cooperation from once it's broken. So it's considered as less pro-social and less interesting from a cooperation perspective. But yeah, no, there is like many strategies. I mean, there are also strategies that are not equilibria, but that you could consider, you could randomize. This game has been studied en long, large, et en travers, as we say in French. There was a question in the back from the beginning also.
So does this work suggest some mechanism for legislation or something like that?
Yeah, I think that's a very good question. Regarding legislation, before legiferating, I guess in English, you want to audit. So because at this point, these pricing algorithms are really black box that are protected under basically the fact that corporations don't want to share their product and don't want to share their secrets. So if there are a good argument in favor of actually we should audit these algorithms to make sure that they are not colluding, that would be the first step. That's what Emilio is fighting for, to convince basically the European legislation to at least be able to audit. And once you are able to do this, you can kind of go to the next step, either legiferate or just, it's fine, actually, these algorithms are not colluding, etc.
And thank you for the talk. And I'm just trying to understand what is shaping strategy and also how it helps cooperation more. So as far as I understand, we pass very quickly. So sorry,
Yeah,
if my understanding is not correct.
I think that's 100% fair.
Yeah, my understanding is that you try to change your strategy to influence your opponent's strategy that will maximize your rewards, right? So for example, if we have two coffee shops, one coffee shop can start as like cooperative. So it teaches the other coffee shop in a way that, oh, cooperation is nice, like we are both good, but then increases its price all of a sudden, let's say, and then starts to earn, like exploit the cooperation of the other. So is it like a shaping behavior?
Yeah, exactly. So it's the thing that, because if you look at your gradient with only respect to your parameters, you kind of you fix the opponent, you consider the opponent as fixed, and so you try to maximize your reward. But if you take into account now that the fact that the opponent will change consequently to yours, it's maybe you may change in a different way. Like you want to basically maximize your reward, first order approximation under the opponent fix, but you want also to take into account the fact that by changing, the action of your opponent will change, which will affect you. So exactly what you say. If I increase my price, my opponent might increase their price themselves. So this is like kind of this other things to take into account. And so in what's really nice is like in policy gradient, it's really naturally emerged from the fact that the Q value of my opponent depends on what I do. So I want, and I mean, I didn't
it's
go
like
through
you'll
this.
have a more sense of control in some way. Like it's determined by your actions. So I feel like if you think in terms of like the agent has more control on determining the outcome in some way, or
yeah, it's kind of so actually there is a nice interpretation of this advantage alignment. So this is the normal advantage. So this is what tells you, what action is good for me at the moment. And this extra term is basically, what's interesting is the sign of this extra term. If it's positive, it makes the action more likely. If it's negative, it makes it less likely. And what happens is that you see the interaction between the advantage of the other and what happened to me in the past. So the interpretation is that if the past interaction has been positive for me, I will make the action that benefits the second player more likely. So like positive interaction. But conversely, if the past interaction has been negative, I will make it less likely.
I see, but when we are thinking about the past interactions being in general positive or negative, is it like in like average type of a sense? Because what might happen is my history might be very cooperative and very positive, let's say, but then all of a sudden, like I see one adversarial or like defect, and then that has a more information value on me because it's like a rare event.
So it's history in the sense, actually, all the sequence of actions that led to this current state. Like you average over all this, and that's you.
Okay, I see. Because I was thinking maybe some events have more importance in the history, but
I mean, they will have more importance if the advantage is bigger, yes. But if they are far because of you have also the discount.
Yeah, okay. I see. Thank you.
Thank you. For the sake of time, I think we have like 3 more questions, but I would encourage people to maybe let's do one more. I think you had your hand up the longest, and for the others, I would say maybe you can just talk to Gauthier afterwards.
With pleasure.
I'll make it quick. I just wanted to ask, what happens with opponent shaping in the first setting? Because we know from Forrester's results that opponent shaping leads to tit for tat.
Yes.
And,
it does lead to tit for tat. I think this is that slide. Yeah.
I was talking in the first setting where we have the collusion.
This is the prisoner's dilemma. It's exactly the same thing.
Okay.
So it's just another, like the opposite perspective, because it's the prisoner's dilemma where you want to cooperate. So you want to exchange the suitcase for free. So it learns tit for tat, even though, there are some subtle things going on. It depends when you stop. Like tit for tat, it's kind of it might be a sort of meta-stable equilibrium where you learn to cooperate in tit for tat, but very slowly you because of this oscillation that is bad, you might learn to cooperate in DC because you realize that in DC that's so stupid, I should just cooperate. but then you start to learn to cooperate everywhere, and then that's bad because once you become a full cooperator, you get exploitable and someone will defect. So it's like the learning is often, I mean, I don't have the exact quote in mind, but at least for Lola, this was the case. You learn tit for tat, but after you slowly learn to cooperate all the time, and then you unlearn tit for tat because you become exploitable. So early stopping in that case is important.
Okay, it's great we had so much engagement. Let's thank Gauthier again.
Thank you very much.